So I think the subject is of appeal to you. I mean, the equivariant maps will come to the rescue, but not exactly in the setting that you have promoted. This is joint work with Paul Gorlach, who is now at MPI in Germany. And this is a project that was started with my colleague at INRIA, Theo Papadopoulou, who works in the group on brain imaging. So I will start by explaining a bit the context of this work. I mean, why we came to look at the invariant of the ternary quartics, which sounds a very classical problem, very mathematical problem, and how it arises in this context. So this team, which is headed by Rachid Derich, they have a different, so they look at different problems, and one of them is to map the white matter in the brain. So those are fibers that go from the gray area to the other gray area. So they do that with a diffusion MRI. So diffusion MRI looks into, can measure the diffusion of water in these fibers. And from that, they deduce, they can kind of try to track those fibers and draw those fibers. So the work is not about, what we're going to explore is not this tracking the fibers, but more to detect in some kind of automatic way some degeneracies. So that's by, instead of tracking and looking at the image that you obtain, you kind of try to have some measure, numerical measure of what is a could be a problem. So for that, so the model, the mathematical model, in either for tracking the fibers or for detecting these problems, is how you look at the diffusion. So the diffusion, I don't know the process, but in the end, what they have is they have an approximation at each voxel, so at each little piece of volume element, they have a function that describes the diffusion of the water. So this function is a function on the sphere, centered at this little voxel. So it's a function of free variable, but you have to understand it around the sphere. And the first model is a degree 2 polynomial. So it's basically spherical harmonics behind it of degree 2. So the first model is a degree 2 polynomial, which is basically a symmetric matrix that you can understand as a symmetric matrix. So the diffusion that you can model with that, it's given by this type of forms that tell you, so those are the images of the sphere under your function. And you can see that this kind of can give you some direction of the fiber, or some kind of maybe, but if you have a crossing of 2 fibers or 3 fibers, it will give you something which is either flat for 2 or like a big blob for 3. So with some additional technological progress and a bit more mathematical modeling, they were able to go to degree 4 polynomials. And what they want to extend is these markers. So for the degree 2 model, clinicians came up with markers with kind of numerical values that they can estimate and that can make, they can detect some problems with the fibers. Don't ask me why. So these markers, they are the, so if your model is this symmetric matrix, these markers are the sum of the eigenvalues. And here this function, which is lambda bar is the this first value, and this other thing. So, I mean, for us, we immediately recognize that these functions are invariant. They are invariant under the action if we transform this matrix. If we take a congruent matrix, we obtain the same values. And actually, this, you can see that this lambda bar is just the trace, and this other value, A, is also something that can be expressed in terms of the trace, and the trace of wave, omega square. So, when we go to a higher degree model, that is a degree 4 polynomial, so now the shapes, the deformation of the sphere that we obtain with such functions, you can see that they can model more intersection. That's why they want to do that. And so this is basically the type of maps that they get. I mean, so I took some pictures from the PhD of Orobat-Ghosh. So at each little volume, they kind of estimate some degree 4 polynomials that they represent with these little pictures. And so what they want to, from this degree 4 thing, they want to suggest to clinicians some values that could be useful as markers. And so these values, it's kind of makes sense that they should be invariant under the action of the orthogonal group. So that's what we are going to look at. So we have a 15-dimensional space on which the orthogonal group acts, and we are looking for the invariance. So they have already tried with kind of a brute force, but kind of cleverly done brute force method for this invariance. And they have kind of shown that it can be useful. And they have even gone to degree 6 polynomials. So when they came to the points where they had many invariants, but they didn't know which one were independent of each other. They were running into problems, and they didn't know when to know if they were generating or if they were complete, just complete, whatever that meant for them. So let me describe a bit more what is the action that is happening, and I just want to impress on you that those are hard computation, basically. So the action, so x, y, z, this is the where this action is taking place, is can be rotated, but kind of like when the head of a patient is rotated in some sense. So here I've written this rotation with the quaternion parametrization. You can use it with, you can use the Euler. I mean, there are many different parametrization of rotation, but I like the algebraic one. So if at some point you have measured if you have modeled the diffusion at 1 voxel by this polynomial, so that is by this 15 coefficient here, if you rotate, if your image was rotated, then you would have obtained this other polynomial with this coefficient omega tilde. And the relation between omega tilde and omega is given by a matrix whose entries are polynomials in this ABCD that came to describe the rotation, but whose are degree 8 polynomials. So you have a 15-dimensional space, a degree 8 action, and you're trying to find quantities which are invariants. So by brute force, you can quickly find that there is a linear invariant, degree 1 invariant, and then you can look for the degree 2 invariant, and that becomes already a little bigger, and then if you go for further invariant, it becomes quite a huge computation. And there are at least 12 of those invariants, and this is just obtained by saying you have 15-dimensional space, you have a three-dimensional action, a group action, three-dimensional group acting on your space. So it has to be at least 12 invariants, but there could be more. So on Saturday, we'll have 2 talks on a related group action by Boris Kolev and Mark Olive. And so from their results, you can actually show that if you look only for polynomial invariants, as a generating set, you will need 64 polynomial invariants. And they actually obtain those invariants, but in some kind of in a way that comes from classical invariant theory as transvectants. So it's all nice. The question is, how do you evaluate this invariant on data? And can you do it in a kind of stable way? So I have been kind of promoting myself rational invariants that come to the rescue to several problems in nice ways. And so we will be looking what is the situation if we look at rational invariants that can simplify the situation. So so this was about the introduction of why I'm going to do what I will present. And now we're kind of coming down to just the math, yes. So we have a small introduction now on rational invariants. So if we have a group acting on a big space omega, so here omega are the space of degree 4 polynomials. It's a 15-dimensional space, and we have an action that I have described of the orthogonal group on this space. So a function is invariant. A rational function on this space is invariant if it is constant on every orbit of the group. Okay? So a good feature of rational invariants is whatever is the group, the field of rational invariant is finitely generated. So this is not always true for the field for the ring of polynomial invariant. So that's already a good feature. And another feature that is of interest is that if you have a generating set of invariant, a finite, so it can be finite. It is always finite. It separates orbits. So it comes, Peter Olver spoke of the equivalence problem. So without the differential and without the manifold, this rational invariant kind of decide of the equivalence in the sense that if you have two objects, they will be in the same orbit if and only if the invariants agree on these two values, on these 2 points, on these two objects. Okay. So this is an if and only if, nonetheless, outside of some lower dimensional variety. So for most omega and mu, they will be on the orbit, on the same orbit, they are equivalent if and only if the rational generating set of invariants agree. And it's an equivalence. If your rational invariants are separating, they are generating. So that's why, I mean, it's because of this property that these biomarkers, I mean, that the invariants are relevant to the application we have. So the mission we are going to address for the specific action that I presented is that we're going to figure out a minimal set of generating invariants, so compute it. We will give a fast and reliable way of evaluating these invariants that we will produce. But then there is another little problem that my colleagues wanted. So in order to be able to provide some analysis of the data, we want to, if we provide some values to these invariants that we are going to compute, can we show from what type of data it's coming? So the inverse problem. I give you values of invariants. Can I say what is the degree 4 polynomial that it's coming from? So we will have an answer to that too. We will also be able to rewrite any other invariants in terms of a generating set that we have. And actually, we will be able to extend our construction to any degree. We will provide invariants for ternary form of any even degree. So we have, so the work that I started with Paul, we had two starting points. On one hand, we are using this decomposition of the ternary form in terms of in two invariant space. So this first space is the set of harmonic polynomial of degree 4. It's so by harmonic, it's exactly what you think. It's the polynomial that are zeros of the Laplacian. And the other piece are all the degree 2 polynomial multiplied by this invariant. Okay, so these two sets are invariants. And the other ingredient was this very general algorithm that computes a set of rational invariants for a group action. And in this algorithm that I'm not going to describe, like in the moving frame, you have you introduce a section to the orbits. And it's the choice of this section is quite free. Some sections are better than others. And it was the natural section for the action that we have here had this additional invariance property under a subgroup, and we were trying to use exactly this property that was going to help us produce these invariants. And it's, so those are the key ideas of this algorithm, and I'm not going to go through that. So this key idea of this invariance of a section was what we discovered to be known as the slice method. So the slice method is, it's basically the slice lemma. It's something that has been used to prove the rationality of some fields of invariance. I think it's the first time that it is used computationally. But this is exactly what we had in mind, actually even more than what we had in mind. So let me present this slice method, which is more general than the action that we want to look at. So we have an algebraic group that acts on a big group omega. And we're going to take lambda, which is a section. So by section, we mean that every group orbit kind of intersect this subspace, at least all the generic orbits intersect this space, but we ask something else. We ask that if an element in this section has its orbit has another point of intersection with this section, then the way to go from this point to the other, it can be done with a group element that belongs to B, to a subgroup B, which is exactly the group that leaves this section invariant, the subgroup that leaves this section invariant. So it's a slice is defined for a subgroup B that leaves this slice invariant, and really it's the only thing that leaves this, any points of this thing invariant. So if you have an invariant of your group, of your big group acting on your big space, if you restrict it to this section with this nice property, then it becomes an invariant on this slice according to the smaller group. Okay, so that's easy to see. And what the slice lemma says is that this restriction, this operation of restriction, is actually an isomorphism. So the field of rational invariant under your subgroup on the small space is isomorphic to the field of invariance of the big group for the bigger space. So that's I think that there are several occurrences of this lemma. I believe that the first time it was mentioned is by Sheshadri in 1962. So let me explain this. Let's apply this slice lemma on the set omega of symmetric matrices. And the slice we're going to use is the set of diagonal matrices. And so lambda is a slice, sure. For any symmetric matrix, omega, we can find an element, an orthogonal matrix, such that by congruence, you take your matrix to a diagonal matrix. Okay, so it's a section. So what is now the group B that leaves this section invariant? Well, I mean, you take a diagonal matrix and look at its congruent matrices that are again diagonal matrices. So for sure, you can kind of find the Q can be the permutation matrix that will exchange this lambda 1, lambda 2, lambda 3, these diagonal terms. So we have a symmetric group for sure in there. But then you have also something else. So if in Q, if Q consists is a diagonal matrix with some 1 and minus 1 on the diagonal, then you will actually leave completely invariant this matrix. So we have, in addition to the symmetric group, we have the sign changes that also appear as a stabilizer of my slice. So this group is known as B3 in the Coxeter classification. It's also the group, also known as the octahedral group, which is the symmetry, the group of symmetry of the cube. So it has a number, I mean, it comes in several places. All right, so let's, so that was lambda is a slice. Now let's see what the slice lemma tells us on this thing. So the invariance of the small group on the diagonal matrices, I mean, so this actually doesn't act, the sign changes don't act, so you just have this permutation group. So the invariants are, you can take the symmetric function, but you can also take the Newton sums. Here they are, the sums of the powers of lambdas, And so you can, the slice lemma tells you that they are in one-to-one correspondence with invariance of O3 acting on the matrices, on symmetric matrices. Well, you can recognize things. Here, this is the restriction of a trace. This is the restriction of a trace of a matrix to the square, and same thing here for the cube. So we know that this is a generating set for diagonal matrices under B3. So we know that this invariance here forms also a generating set for the set of all symmetric matrix under O3. So that's the consequence of this slice lemma. So now, so this was for symmetric matrix. As I told, I mean, as we've seen, as you know, symmetric matrix, it also models degree 2 homogeneous polynomials. So we have the results. We have a nice result for, we have reproved, re-seen in a different light the case of degree 2 polynomials. And so now we're going to move to degree 4 polynomials. And we are, thanks to this slice lemma, we are first going to look for the B3 invariant on a slice. So our big space, degree 4 polynomial, we saw can be split into the harmonic polynomial and the degree 2 polynomials. Degree 2 polynomials, we figured out the slice. This was this diagonal matrices, lambda 2. So now a slice for my bigger space is this lambda 4, where I'm just adding the harmonic polynomials. So the way we're going to have invariance for B3 is by introducing the appropriate basis, a B3 friendly basis for H4. And so this basis consists of 3 blocks, the R block, T block, and U block, which are span spaces which are invariant and on which the action of B3 is kind of nice. So you see that R2 and R3 are obtained by R1 by a cyclic permutation of X, Y, Z. It's true for the other blocks too. Now, if the sign changes, if you change the signs of x, for instance, here, you will change the size of T1. And if you, same thing here, when the sign changes don't affect this one, this piece. And an additional thing here, if you use a permutation, if you use a transposition, the sign of u is going to change. So you have a little change, so it's the action of B3 is relatively simple to describe on those bases. So let me write it again. I will re-explain that, formalize what I just said. So if I have a degree 4 polynomial, I can write it in the basis I just gave. So degree 4 polynomial on the slice, so I have only this quadratic term. Now I have the coefficient rho 1, rho 2, rho 3 for the parts which depends on r, and then the tau and mu. And I'm acting on this polynomial with an element of B3, which is a sigma, which is a permutation, and psi, which is this matrix, which is a sign change. So this action will produce a polynomial with coefficient rho tilde and tau tilde, mu tilde, and the relation between the tilde variable and the non-tilde variable is given by these changes. So lambda is just changed by permutation. Same thing for rho. Now tau is changed with a sign change, a bit different, and this mu is not only as a permutation, as a sign change, and also here comes the signature, the sign of the permutation. How do you say signature or sign? The signum of the permutation that comes here. So we are looking for invariants of B3 on for this action. So the ingredients we worked with were some result by Dalbec on multisymmetric functions. So those are polynomial functions this time. So we worked on we computed this function that they are given in this paper, and then tried to take off all the redundant information. So that was massive computation. And on the other hand, we applied this general algorithm, and by trying to match the two results, that's when we came up with the nice formulation when we saw the structure in these invariants. And this is the structure I'm going to present. So here we have this coordinate that I give you equivariant maps. And we are going to produce more equivariant maps so that combining them, we will produce the invariants. So we're going to have equivariant maps that are where only the equivariance is given only by the permutation. So the first thing here, here those are exactly already in how we want them. For this tau variable, we can introduce the squares, and that will remove the sign change. And for this variable, where you have both the signum of the permutation and the sign change, well, sign change we are going to fix by multiplying with these variables. And the signum of the permutation we are going to fix by introduce this quantity, lambda bar lambda, which is this thing here, which is also the determinant of this Van der Monde matrix, which is also an equivariant map as we want it. So now we have all these equivariant map for this equivariance. So if we take the transpose on one of this map multiplied by the other one, we get an invariant. So it nicely produces some invariants from the equivariant maps. So that way, so with this, for instance, if we take this Van der Monde matrix, transpose it, and multiply by this 3×4 matrix, we obtain 12 invariants. So the entries of this product matrix are all invariants. And we can show that if we add this little product, like the product of tau1 to tau3, we get a a complete set of invariants, complete in the sense that it's generating, and we can also write the rewriting rules to rewrite any invariant in terms of these. So what I think is really cute is that we can write them in a very compact form. So that's really the neatest thing, especially when you have seen, when you started with big expression and the wallpaper type of expression that we had at the beginning. So that's really nice. So here I said, that we had at least 12 invariants. That was just a dimension count. If you see it here, we have 13 invariants. So we are not far from the very, very minimal possibility. And actually, by twisting things a little bit around, we get this minimal number exactly. So instead of the Vandermonde of the lambda, we use the Vandermonde of the tau square. And here we have the same columns. So this is a set of 9 invariants. So that you take the product of these two matrices, that gives 9 entries. These 9 entries are invariants. And what you need to add are those invariants. So I took the elementary symmetric function in tau square. So you have 1, 2, and instead of the third one, you have this product. So that's the minimal set of generating invariant for B3 on the slice. Now we need to come back to the O3 invariant on the bigger space. All right, so the slice lemma, so we have computed this invariant for B3 on the slice. By the slice lemma, we know that there is the exact same number. These invariants are in one-to-one correspondence with O3 invariant on the bigger space. And they are uniquely determined by their restriction. So we devised some kind of grand plan to obtain this, the expression of these Qs in some kind of organized and structured way. But if you think about it, after we get this big expression for the Qs, how do we evaluate them? Having the expression for these Qs, does it give you a good way of evaluating them? And I doubt it. So here is the numerical recipe to compute these invariants. So, well, if you have a polynomial, a degree 4 polynomial, so basically you know it by its coefficient, and hopefully, and not hopefully, you make it in the basis that I explained, this B3 friendly basis. So you can split it into the part which has a degree that corresponds to the quadratic part. You compute a matrix Q in O3 that will diagonalize this quadratic part. So this Q is not unique, but we don't care. Any of the matrix that diagonalizes will work. So we get this thing. So now with this matrix Q, we kind of rotate all the data to obtain another degree 4 polynomial. And then the value of your invariant on the original degree 4 polynomial is given by the value of the B3 invariant on this obtained data, on this rotated data. Independently, and because P is this B3 invariant, it's independent of which Q you have. So I'm not going to make a wallpaper of this expression here, of these Qs. I'm just giving you how to evaluate them. Next, I'm going to tell you how you can rewrite any other invariant Q of O3 in this invariance. And that's just that you restrict Q to lambda by putting some things to 0, some coefficient to 0. You express this restriction, so this restriction is a polynomial, a B3 invariant on the slice. So you can write it thanks to this formula. in terms of your B-free invariants. And this function f that you use to do that is exactly the function you're looking for. And so rewriting the B-free invariant, I mean, as I said, you know, it's nicely, it can, you can prove that this is done with this explicit rewrite form. So the inverse problem that I mentioned earlier, it's also possible to do it, and there is no big results there. It's just because we have the invariants we have a very nice shape, and in particular they are nearly kind of linear, and they are linear in many of the variables. So if you give yourself, so you give your values for all the invariants. So first the invariant in tau, they were these kind of symmetric functions. So if you compute the roots of this polynomial, they will be exactly the tau1 square, tau2 square, tau3 square. So you obtain this first piece of information. So then you kind of solve, and then you just have to solve a linear system that will give you the other values of your other components of your degree 4 polynomial. So that's the inverse problem. The question is when do you get something that is real and something that is positive? So real we can answer, positive is not clear. So the next thing is to do a higher degree polynomials. Can we find the invariants for the action of all three on a higher degree, even degree polynomials? Well, the recipe is, the result is that, so first you do this harmonic decomposition, and here the big result is a new set of bases for the harmonic polynomial, which are B-free friendly in the sense that my R, S, and T are. So this is a construction for all D in a higher, so for all D we can construct these bases. It's fairly explicit, there are even closed form formula that I'm not going to present. And once you have this, I mean the result is really that, is really finding these bases, and once you have this equivalent basis, you just combine in the same way that I did earlier to produce some invariants, and it's obvious that it's kind of obvious that they are generating. And so you obtain a minimal set of generating invariant for any degree. The work in progress is to how do these nice invariants that we have can actually help in the analysis of the data. So this is in practice. I mean, this is where my colleague now is leading, is how to, my colleague in the brain imaging team, is putting these things in practice for the moment on synthetic data. So hopefully I can report on some of that later this year. Another theoretical question is to describe the orbit space of positive quartics, but that seems amenable. And that's the end of my talk. It's a big thanks for listening to me before lunch. And the paper is available on Archive and AL, and just accept it for publication. Thank you.
So are there questions?
So your rewrite rule requires a rewrite rule under the discrete action of the slice group, the slice isotropy group, right? And
sorry?
So to do your rewrite rule, you first need a rewrite rule for your slice invariants.
Yes.
So was that done by hand, or does the machine work for, say, your method with ARENA? Does that work for the discrete, for the finite groups? to get a rewrite rule there.
Oh yes, I mean, so yes,
Yeah,
so
so
it's
that-
how we got them.
Yeah, so that's
It's
how
by
you got, that's what I
applying,
was asking, whether it
yes.
was ad hoc or
Yes,
systematic.
so we wrote so the invariants I showed, they are generating. So we can can rewrite what comes in this algorithm by Irina and myself in terms of those invariants, and then you get the rewrite rules. So let me say it again.
Yeah.
So the algorithm with Irina provides rewriting rules. And these rewrite rules can be deduced from the Grosvenor basis of the intersection ideal. Okay. And the coefficient of this intersection ideal, it's where you read the invariants. So now we have a generating set. So all the coefficient of this Grosvenor basis, we can write in terms of these things here. So the rewrite rules can be written in terms of what we have. So my thinking is always by using this algorithm, yes.
Are there other questions? Well, if not, thanks again.